how to solve the general problem in the first order differential equation. If you remember, what we were doing yesterday was separating variables, but the thing is that the variables won't always separate. And we had problems, the first ones, 5, 6, 7, 8, were ones where you wouldn't be able to solve those by separating variables, but what we practiced with was how, if they gave you a solution, you could tell that it met the initial values or not, and you could tell that the solution that they gave you to look at would actually work, because you could substitute in and see that the left-hand side would equal the right-hand side. And so now, for the general problems, you go like this. Some definitions here. We talked about linear yesterday, but it's an important concept, so let's review that again. So the differential equation is linear. I'm thinking of it as if y is the variable when all of the following happen. The differential equation might be higher order than the first order. Remember, the order from yesterday is the highest order derivative that appears. The differential equations in this class in your book are all first order, but many that are important are second order. And clear over at the right, I have the second order differential equation for an electric circuit where the charge is the variable, for example. So whatever order it might be. To be linear then, the y prime, y double prime, whatever there would be, will appear only to the first power, and or else they don't appear at all in each term in the differential equation. So first power, by that I mean if you had a y square, that's not linear because the squaring is not. If you had 1 over y, that's not linear because that's y to the minus 1 power. If you had square root, that's y to the half power. So anything like that makes it a nonlinear differential equation. The method that we're getting at here applies only if it's linear and first order. In addition to list the requirements to call the differential equation linear, you don't have any more than one of y or y prime or double prime or however high the derivatives might go in any one term. So that means if you had a term y times y prime, that makes it nonlinear. And you can't get away from that by, say, dividing by y, because that means there'd be terms then where you had 1 over y, or y to the minus 1 power, and that's still not linear. And then they don't appear as the argument of any function other than the first power function. So examples of nonlinear terms would be 1 over y, where you see here the y is the argument of the 1 over function. Here it's the argument of the square root function. Here it's the argument of the square function, or of sine, or the exponential, or the log, and on and on and on, of course. So if you have anything like this in the differential equation, it's nonlinear. That doesn't mean necessarily that you cannot solve it, but it means you don't solve it the way that we're about to talk. Okay? So the linear first order then, for some interval I, would look like this. You see, it's perfectly fine to have coefficients in x that are complicated functions. You can certainly have sine x there, or e to the x, things like that. But the y, you see, it's first power, and only once per term if it's there at all. So the general situation is perhaps some messy expression involving x times y prime, another one times y, and a third one over here. Also, if it is first order, that means this term is always there, so this coefficient isn't zero for any x in the interval where you're claiming to get a solution. Because if it is zero, then your first derivative's gone and you don't really have a differential equation anymore. So you have that restriction on it. So in order to construct what we call an integrating factor, which goes back to somebody in the Bernoulli family, as I've said, I think more than once, there were several related people named Bernoulli who had apparently kind of a family competition as to who could come up with what in inventions related to calculus and therefore differential equations. I'm not sure that people even know necessarily which Bernoulli did what. But anyway, they came up with the idea of what we call an integrating factor. So to do this, the first step is to convert the original problem to what we call standard form, which means that you get coefficient 1 on the y prime. And you can do this because our assumption is that whatever we started with is not zero on the interval where we're to work. So therefore, if it's not zero, you can divide through. So that means that what we're calling P of x is B over A, and what we're calling Q of x is C over A, as I said. People use the Greek letter mu for this integrating factor. I don't know for sure whether that's what the Bernoullis did or somebody else did, perhaps like Euler, for instance, but it's what everybody does. So the integrating factor that works is that you take the integral of what we're calling P after you're in standard form, and then take that power of E. And if you do that, and then multiply all terms in the standard form by e to the integral of P, your left-hand side, which would be this e to the integral of P times y prime, plus this e to the integral of P times y, is always the derivative of a product. So that's the integrating factor game, that if you construct this factor, multiply standard form by it, you now have a differential equation where the left-hand side is the derivative of a product, where the solution you want is one factor. So this derivative of a product equals the new right-hand side. If you're multiplying by mu here and there, you have to multiply there. But you see, now you can get your hands on y, assuming that this product here is something for which you can do the integral. And in all the homework problems anyway, it will be. So you can slap an integral sign there and there, and the integral of the derivative of something or other is just the something or other. So you get, see, that's my step 4, the integral of the derivative of the product is going to be the integral of the right-hand side. So this is automatically the fundamental theorem of calculus going to be the y times mu of x, and this has to be an integral you can do. And if you can do that, then y will be this integral over your integrating factor. You notice that your integrating factor would never be 0 because the power of e is never 0 for any finite value. So there's not any problem saying then that y is this integral over the mu. The issue would be whether or not this is an integral you can do in the sense of this class, but in all the problems you have, it will be. And then if you put on a plus constant, and then if you have any initial value, you can use that to determine the constant. So a definition then, the word exact. We call the differential equation exact when the left-hand side has the form derivative of a product where the function that you're trying to get is one factor in the product. And some of them are exact the way they're given. Sometimes you can just look at it and see that your left-hand side, like problem 1, is already the derivative of the product. If it is, just recognize it and write it that way, and then you don't have to do all this. So take a look at this left-hand side and think about it for a second, and you see it's the derivative of x times y, because think of your product rule. You have the left, look at the factors, x and y. You have the left times the derivative of the right, plus you have the derivative of the left, which is 1, times the right. So this is the derivative of xy. See, I wrote it out down here. X times the derivative of the right plus the derivative of the left times the right. So then this thing is exact, as I defined the word, the way it was given. That's a happen, so it's problem 1 after all. And so you can say your left-hand side is the derivative of xy, and slap on the integration symbol, which would be the integral then of the right side plus constant. Okay, the integral of the derivative of something is the something. Here the integral of e to the x is e to the x plus constant, so then you can solve for y, and that would be your answer. Now, if you go through this drill with problem 1, you'll get to the same place, because what you'll do, you see, if you go through the drill, is, first of all, you divide by the coefficient here, if it isn't 1. And then, when you do that, you'd have 1 over x right here, so that's the p that I have talked about here. The p is the coefficient over this, 1 over x. Then the integral of p is the integral of 1 over x, which is log x. Then e to the log x is x. So you would have divided by x, found p and then mu, multiplied by it, and it would have taken you right back to here. Because you'd have divided by x, and then x turns out to be the integrating factor, So you multiply back by what you had divided out, you'd be right back to this point. So let's look at one where you actually have to get the integrating factor, where the thing wasn't exact to start with. So look at problem 3, okay? Not standard form, so you divide by the coefficient. So divide by x all the way across, including over here. And this is p right here. Whatever you get when you divide by what was there as the coefficient of y, that's what you call p. That's going to be a function of x. The constant is a function of x. So it's a true statement that your coefficient of y is a function of x, and you can call it p if you want to call it that. That's what the book does. And so then you integrate, which would be, integral here would give you the 3 log, okay? And then you use your general power formula that for any base a to the u is e to the u log a. That's true because the e function and the ln function are each other's inverse. That's all it is. So when you construct p, the Bernoullis came up with the bright idea that the integral, that e to the integral of p would be this integrating factor. And so what you would do then is take e to the integral of p, 3 log x, or if you wanted, it's log x cubed, you see. You can put the 3 up there if you prefer it. Either way, x cubed is what you get. See, the reason x cubed is what you get is that if you rewrote this e to the log x cubed, then e and ln are each other's inverses. So e to the ln of anything is the anything. So the integrating factor is x cubed. So you multiply your standard form, not the original, but the standard form, by the integrating factor, all the way across. So you have x cubed times y prime plus 3 over xy is x cubed sine x over x cubed. You notice that cancels. That's the light at the end of the tunnel, you see, which is, for us at this moment, not the headlight on the train that's going to get you, because this cancels, so there's hope you could really do this integral. Okay, now what about this side? This is the derivative of the integrating factor times y. You can check your work. See, I'm saying it's always going to be that, but check. You have the left times the derivative of the right, that's that term, plus the derivative of the left. What would that be? That would be 3x squared. See, if you multiply this through, you have 3x cubed over x, that's 3x squared. That's the derivative here, times the y. So this is the same that this would be. That's the gain, you see. That's why this is worth something. So now the derivative of this product, where y is one of the factors, is sine. So slap on the integration. The integral of the derivative is the inside argument. That's your fundamental theorem of calculus. So x cubed y is the integral, which is over here, is the integral of sine, which is minus cosine, plus constant. Now you can solve for y. Right through. The reason that you have to assume that the x was positive was in order to say that the integral here of p is 3 log x, because your log, the domain of the logarithm is positive. So that's what I've said down here. Now, if you had an initial value, you'd use that at this point to get a specific value for c. This, you see, gives you a family of integral curves. If you were here yesterday, you remember we had the maple handout and the idea of the integral curves. So there's an integral curve for each choice of c. And in the maple handout, we made various choices of a point that was to be on the curve, and that gave us a yellow graph in the field of all the red arrows. Okay, so we have no initial value given in problem 3, so this is all we can do. But these over here are initial value problems. If you look at 16, you see there's an initial value, y of 2 equals 1. So we look at this one. Again, this is not exact as it stands, because but we can go to standard form and divide by t, which we're assuming is not 0. That gets this, which is our standard form. And then we will look for an integrating factor to apply to this. So the p is always the coefficient of the y, complete with whatever sign is here, as you'll see in I guess it's problem 18. You notice in 18 there's a minus, so if there is a minus, like in 18, that's part of the p. Okay, so back to here then. The p is plus 2 over t. The integral is 2 log t. And so the integrating factor is e to the 2 log t, or e to the log t square, which is the same thing, and then e to the log t square is t squared. So you multiply standard form by the integrating factor, not necessarily the original, but the standard form. And when you do, the left-hand side would be the derivative of the product of y and the integrating factor. You see, you can check your work again right here, because the derivative of, well, you'd have the left factor, the t squared, times the derivative of the right, plus the derivative of the left is the 2t times the right. So this left side is derivative of t squared y, and the right side, when you multiply the original t squared by the integrating factor t squared, is t4. The 4 seems to be a little worse for wear. Okay, so the integral of the derivative, which is t squared y, is the integral of t4, which is a t5 plus constant. So now I would use my initial value before I do algebra to solve for y. You can do it either way, but what I'm going to do then is say that when t is 2, the y value is 1. So I'm putting 1 there and 2 there and squaring it. 1/5, 2 there and raising to the 5th power plus constant. So this is 4 minus 32 over 5. Get a common denominator, so it's minus 12 over 5. So then back to this line, t squared y is a 5th, t5th, constant is minus 12 over 5. Solve for y. And that would be, if you wanted, noted that you have the common denominator, that would be t5th minus 12 over 5t squared. So you could write the answer like this, or if you prefer, you could divide the t squared, and you'd have a 5th t cubed minus 12 over 5t squared, which is the way the book has it. I don't believe that answer is any better than this one. That's one of the troubles, I think, with my math lab type things, where the computer is programmed to look for one form only for an answer, and another form is just as good. So anyhow, look at 17. This is the Greek t, the theta. And again, you see it's an initial value problem. So go to standard form again, divide by the theta. And so this is your p, integral is log theta. Your integrating factor then is e to the log theta, which is theta. You notice when you multiply this by theta, you're right back to here. So the point is that the left-hand side here actually was exact, the same as it was with problem 1, which I have lost, but it's here, okay. This one and that one are the same kind of thing. Here the letter was x times the derivative plus the function. That is the derivative of the product of the x and the function, right? Which I pointed out half an hour ago. This is actually the same thing. You have your variable times the derivative plus your letter name for your solution. That is the derivative of the product of the variable times the function you're trying to get. So if a person wanted to do so, you could have skipped this because you could skip from here to saying that the thing is exact and that your left side is the derivative of theta times y. So that equals your right-hand side. So then you integrate, and when you do integrate the derivative of this product, you get the product. You integrate the sine and you get minus cosine. And then you can solve, then you can use your initial value. So when theta is pi over 2, y is 1. So the numbers go there. Cosine pi over 2 is over here. And cosine pi over 2 is 0, isn't it? So pi over 2 equals your constant. And so your theta times y is minus cosine theta plus pi over 2, and then you can solve for y. Okay? Now we better do this. Start 18 over here. Notice that there is the minus, which is going to be part of the heat. the P then is not 2, it's minus 2. And notice it is 2, it's not 1, so this one does need the integrating factor. This is not exact because the derivative of the variable times y looks like this with a plus here and a coefficient of 1. And this is a minus and a coefficient of 2. So divide by the theta. This is our standard form. And then the p, as I've been saying, as the minus. So the integral is minus 2 times the integral of 1 over theta, so minus 2 log theta. Notice that's theta to the minus 2 power in your rules of logs. So e to the log of theta to the minus 2 would be theta to the minus 2. So the integrating factor is 1 over theta squared, theta to the minus 2, as I've written it here. So now what will happen is that 1 over theta square times your standard form line, this one, not this one down here, that'll be exact. So I've written it here, and you notice that it cancels the theta square over here so that you can feel encouraged about doing the integral on the right-hand side in a minute. So this now is the derivative of the product, all of it, because your integrating factor makes it so. And so it's the derivative of the product of 1 over theta squared times y, or it's y over theta squared. So then you slap on the integral signs. So the integral here is what you have the derivative of. That's your fundamental theorem of calculus again. And the integral of secant tangent is secant plus constant. And you have your initial value. So now put in your initial value. Remember, it's always radians in calculus, so the theta is the pi over 3 radians, so it's squared. Cosine of pi over 3 is a half, and secant is 1 over the cosine, so it's 2. That's how I think it through. I never can just remember cold what values, the exact values are for secant and cosecant, but I can remember them for sine and cosine, and then I can invert the fraction. So anyway, and then you have 2 plus constant. This is pi square over 9. So what you have with your fraction here is 2 over 1 and over pi square over 9. So you invert and multiply, so you have 18 over pi square minus 2 for your constant. Or you could get a common denominator. So then your y is theta squared secant plus your constant, which is here the 18 over pi square minus 2 times theta squared. That's the way the book has it. You could instead have said theta squared secant and written your constant like that times theta squared. If I'd been doing it, I think I would, but this is certainly not wrong. Same issue. Okay, so now let's start looking at some applications, and most people got this, but a couple people didn't. Applications handout, then I have on the board for today, and we'll be continuing with it on Thursday next week. But first of all, one of the important applications of a first-order differential equation is exponential growth or decay. And in a class like Math 143 or 147, they just give you the formula, which is the result of solving a differential equation. So the formula that you get to, at least, will be familiar to you. So say that we use n of t as the census at time t. There's no reason mathematically that a census has to be limited just to people. And so the assumption that you make is that the rate of growth, if it is growing, positive k, or the rate of loss or decay, if the k here is negative, is proportional. Now, proportional to what? If it's growth, it's proportional to the population that has accumulated at a given time. And this, of course, could be money at compound interest just as validly as its people, say, or any other kinds of critters. And if it's decay, that doesn't have to be radioactive decay, which is probably what you think of first, because just as importantly to people, it applies to metabolizing drugs, for example. Legal or not, they still metabolize, where the rate of loss is proportional to the level that's remaining, say, that you would find by a blood test or a urinalysis test if it's drugs, or if it's radioactive, the count that would remain. So the K then is what we call a rate. A rate doesn't always have to be a time rate. It is a quotient of units of whatever your function is measuring over units of whatever the variable is that your function depends on. So, for example, a spring rate can be pounds per inch, where it's pounds of force required to stretch a spring or compress a spring, that sort of thing, as in Hooke's law, for instance. So here, say, your rate of units of whatever your census is counting over time. So from your differential equation that you have, you can separate variables. So divide by the n, multiply by the dt, and then you can integrate both sides. You don't need to use the general first order procedure for something when you can separate variables. And your integral gives you log, and your integral here gives you kt plus constant. So then if you want to, this is the logarithmic form of your solution. And there's nothing mathematically wrong about it as far as saying that's a solution, but usually you want to solve for n and go to the exponential form. So what you're saying is that e is a function, and therefore if it's a function and you put on equal exponents, you get equal values. So e to the log n is n equals e to the kt plus c, which is here, constant c1, and then you can play games, because the laws of exponents, when you multiply powers of e, you add exponents, so you can factor when you have exponents added or subtracted like that, and then e to the c1 is just another constant you call c. So your general solution then is your census is a constant e to the kt, where this again is the growth or decay rate. And for an initial value problem, you'd say that n subscript 0 is your census at time 0. That's the usual way the information is handled. And so therefore, then this constant, you see, if you put 0 there, you have e to the 0, which is 1, and this constant equals the n at time 0, which I'm calling n0. One thing that you usually want, if it's growth, is the doubling time, and if it's decay, you want the half-life, as the chemistry department calls it. So capital T is the doubling time. So that's the time when the n is twice the n0, whatever it is. You see, the time depends on this rate and doesn't depend on what this actual count is. In other words, it's the same length of time if you're thinking of money at compound interest for $100 to become $200 put out at interest, as it is for 100 million to become 200 million. Now, that's true mathematically, but in the real world that's false, isn't it? Because if you have $100, you can't leave it alone, number one, and number two, as a person, an ordinary person such as I am, I won't speak to any of you, all that's available to you to invest $100 is some kind of bank savings account that pays no interest. Whereas if you have $100 million, you can make deals, and you can really make some money on it. So that's why them as has gets. Well, anyway, back to here. Back to poor people and the math. Then it wouldn't matter what this n0 is, and you could cancel it out. And so you have 2 equals e to the kt, and log 2 is kt log e. Log e is 1, so your growth rate and your doubling time product is log 2. So therefore, if you know the growth rate, the doubling time is log 2 over that. What about half-life? This is the Greek letter lambda. Lambda is when your count is half what you started with. And again, that won't matter, just the half-life on one drink of alcohol or on several is going to be the same amount of time, which is actually about an hour for alcohol. So divide out the n0, so log half, which is minus log 2, is the k lambda log e. So it's the same formula. Notice that log 1/2 then is negative, or minus log 2 is. So this is when the k is negative. So this is the same formula here, just whether k is positive or negative for decay and growth. And another thing that is a decay type formula is various kinds of tax schemes that use accelerated depreciation, so on. So this application of differential equations is really quite important. If you look in the publication that's called the Nurse's Handbook of Ordinary Drugs,
they have the half-life for all kinds of prescription medicine, both blood pressure medicine and all kinds of things that people take. And one of the things that the drug makers give in the studies that are required by the government to approve the drug and so on is what the half-life would be. So half-life is a very important idea in pharmacy, certainly. So look at circuits. So what I'm talking about here is the differential equation for series circuits. So this would be your active element, as it's called, which could be a generator or a battery. If you draw something that looks loopy, that's inductance. If you draw something that's got sharp teeth, that's resistance. So that would be an LR circuit, where I would be the current in amperes, Ampere was a French physicist, so I wrote it with the accent as you would in the French. The resistance would be ohms, German physicist. Resistance is heating, and the inductance is L written, the units are called Henrys, who was an English physicist. And the inductance is the time lag between the voltage and the current if you have AC circuits. If you come into this room and turn on the lights, they come on right away because modern fluorescent lighting systems always have a little current in them even when they're turned off. So you don't notice that time lag. But if you live in a house, as I do, that was built in the 1950s and still has the original fluorescent lights, I turn on my light switch and it takes a while, and then they have to kind of flicker and so on like that, and that's the inductance. And then if you're looking at what's called an RC circuit, the C is farads. Michael Faraday was another English physicist, and that measures capacitance. A charge can build up, a capacitor in a circuit which can alternately charge and discharge. So the constants of proportionality in the differential equations, where the variable is either charge Q or current I, are L for inductance, R for resistance, and 1 over C across the capacitor. The 1 over C has a name that's called elastance, which I wrote someplace. There we go. We call 1 over C elastance. So the differential equation for an LR circuit is L di dt plus Ri equals the output of the active element, which would be volts, say. Volta was an Italian physicist, by the way. And so you see this is a first order differential equation where the variable is the current. There is also one with the charge that enters in if you have a capacitance. If Q is charge, Q is in coulombs. Coulomb was a French physicist, which accumulate in the capacitor. That one looks like resistance dq dt plus elastance Q is the voltage from the active element. These products like LDI dt or RI or RDQ dt, these are volts. These products are called voltage drops. And the Swedish, I think, physicist was Kirchhoff. I think he was Swedish, actually. That means Church Hill, actually. This is Church and the Hoff's Hill. So Church Hill in Swedish, if you like. The laws are that the voltage drops across the passive elements, which are these, the sum of those equals the sum of what comes out of the active elements. So if you put this all together, you get a second order differential equation where the charge is the variable, L Q double prime for second derivative, plus R first derivative of charge, plus elastance charge equals what comes out of the active element, the generator or the battery. And then you have the general situation where if you have the passive element, the L, the R, and the capacitance, the voltage drop across this is LDI dt, or L second derivative charge. Across R, it's RI, or R dq dt, and across the capacitor, it's the elastance times Q. Notice that you can also do the circuit analysis for this kind of circuit with a system of differential equations, because I is dq dt, current is time derivative of charge. Your current is your ampere is coulombs per second. 1 ampere is 1 coulomb of charge per second, you see. So you have one differential equation, really, that I is dq dt, and then the second one here, that R dq dt plus elastance Q is the voltage. So this, you could solve this one for Q, and then you could differentiate your Q to get the current. So in that way, you can get the current that's across here. So sometimes you get a system of first order differential equations where you solve one, and then after you get the one solved, you use that solution, as in this case, to differentiate it to get the other variable. One of the things we'll do next Thursday is a situation of this sort where we solve a system. So I think you can see from this that there's really a lot of reason why differential equations are important to people in physics, engineering, and other branches of science, certainly. And so bring this back with you next week, because we've just really talked about the first sheet of paper in it, and we have several sheets of paper to go through some applications. We'll also do some applications that are in the book, but I think some of these are really better applications. This is something that I go through when I teach the differential equations class, which is why I happen to have it, and so on. So, have a good week.